need to turn this game so. All right, so this is the beginning of our last unit, which is kind of on radioactivity and things nuclear. We're gonna have four lectures on it, and there isn't a whole lot of reading. There's no reading in the text. I'm gonna have one reading associated with one of the topics, but you'll see on this next slide kind of what the topics are. So today we're just gonna kind of review a bunch of different stuff about radioactivity, nuclear stability, units of radioactivity and dose, the energetics of different types of nuclear reactions, and then hopefully that comes back in. Some discussion of fission and isotope enrichment, which is important in the nuclear cycle, both whether we're talking about nuclear energy or nuclear power or atomic weapons, and especially fission products, which are essentially the key component of the safety hazard associated with using nuclear fuel for things. The next time we'll focus entirely on nuclear waste and accidents. This is an interesting topic that varies a lot how waste is handled around the globe. And then we'll have a whole lecture on environmental radioactivity of depleted uranium. That's based on work that I've done here in Hawaii with the Army. And then the last one, whatever that is, May something or other, we'll talk about the environmental radioactivity of radiostrontium and radioyttrium, which is a thing decays into. One of the very first sort of poster child nuclides of the above ground atomic weapon testing era, and strontium gets in your bones and all this kind of stuff. It we'll see is a pretty nasty substance. And unfortunately, even though since the reduction of above ground testing in the mid-60s, it's declined by a lot. It hasn't gone away. And it's something that it can also be released by nuclear power plants. And so we see some persistent issues there. I also just wanted to mention that next time I'll talk with you guys about the final paper. And so I think there'll probably be one more homework associated with these 4 lectures, just because I like to do 4 during the semester and I haven't managed to do them yet. So there'll be something about radioactivity. It won't be too hard, but it obviously won't come out of the text. All right, so I think this stuff is probably review, but I want to go through it just to make sure. We're going to talk a little bit about basics of nuclear chemistry, nuclear reactions, what makes nuclei, etc. We'll talk about the chart of the nuclides and what makes a stable nucleus, the different types of radioactive decay, what we call the nuclear binding energy equation, which relates the amount of energy that hold the nucleons together to their mass. And then we'll switch to talking about nuclear fission and specifically chain reaction and isotope enrichment to get to chain reacted quantities of materials, which for a bomb is a critical mass. That mass is a lot less for if you're trying not to have the thing explode and you want it to be producing power. And then we'll talk about other kinds of fission products and incidental nuclear materials. So there's a lot of irradiation that happens around reactors that makes other things which are oftentimes the more problematic waste materials to dispose of because they're over a much broader area. So I think everyone, right, you guys know this, but we define our atoms by the number of protons. They have different numbers of neutrons. Those are called isotopes. And so a nuclide, which is just another way of saying an isotope of a specific element, is defined by a combination of its Z and its N, protons and neutrons. And all nuclear transformations rearrange the relative proportion of the Z and or N. So it's something that's useful to kind of keep track of. Some things replace both of them, some change one into the other, or in either direction. There are some associated nuclear reactions, which are the emission of photons with gamma energies, which don't change Z or N. They don't happen by themselves. They always happen along with something else. And this is, the atomic mass, the thing that we're familiar with. It's just a combination of both of them. So, think about radiocarbon, which is a radioactive nuclei, and it's a rare form of carbon that's formed in our atmosphere. Much smaller percentage than carbon-12 or carbon-13. It also has 6 protons. That's what makes it carbon, but it's got 8 neutrons. The 6 and the 8 is what makes it 14. And it's the extra neutrons. And in fact, it's formed in the atmosphere by radiation, cosmic ray radiation on nitrogen. So isotopes obviously have different numbers of protons and neutrons. Some combinations are stable and some are radioactive. Okay, so like using this example of carbon, the carbon 12 and 13 are stable, the carbon 14 is radioactive. Those are the ones that, I mean, these are stable, so they haven't changed since Earth formed. 14 is produced on Earth, so we have a standing crop. We've always had it, we'll always have it. Sometimes we have more or less, has a lot to do with the magnetic field and shielding and cosmic ray flux from Earth and the development of our atmosphere. A whole bunch of different things go into how much radiocarbon we have. But there are other isotopes of carbon that exist that we find in stars, for instance, but they're so short-lived that we don't have them on the planet. And that's true for a lot of different chemical elements, have radioactive isotopes that, even though we distinguish things that don't change from things that change, it's also useful to recognize that how radioactive something is, which we measure with a decay constant, the number of decays per unit time, which we'll see in a second, can be related to the half-life. So fast decay constant means a short half-life, and a long decay, low decay constant means a long half-life. So things can have more or less radioactivity associated with them. And again, that spans orders of magnitudes from fractions of seconds to billions of years. And so therefore we have radioactive isotopes that are used all the time in the earth sciences, things like, isotopes that have been produced by radioactive decay of samarium or rubidium or uranium and thorium going to neodymium, strontium, and lead respectively. Those have been around since long before Earth formed, and they're still persistent. The kinds of isotopes that we're going to be talking about during nuclear processes have much, much shorter half-lives. And they decay much more quickly. They decay oftentimes much more energetically. And so we'll see that this is really a spectrum. It's not a binary between stable and radioactive. So this is something called a chart of nuclides. You may or may not have seen this before, but it's basically just a plot of isotopes, Z, the proton number, and N, the neutron number. And these black dots up the middle are the stable nuclei that we find on Earth, or the very long radioactive ones. So for instance, you would find uranium-238. Even though it's radioactive, its half-life is about the same as the age of the Earth, and so we have a little bit of it, okay? There's some other bands on here, and I don't want to go into them in a ton of detail, but this gray band, okay, are things that we have evidence for having been present on Earth in the past, but no longer present now. They're all radioactive, and the way we know that they were present is by looking at the things that they decay into. What we call extinct radionuclides, and really what we're looking at are isotope anomalies of what we call the daughter isotope. And sometimes it's not a simple process of one thing decays to something else, and that's it. Sometimes we'll have one thing decay through a series of intermediates to a final product, and that'll give us an unusual abundance of one or another isotope compared to the other isotopes of that element, and that'll tell us that, oh yeah, we had a certain amount of a live isotope. Now you also see some bands. There's this white band, and there's this sort of hasher turning into chicka-chacka band. And just in the simplest way, the first thing you'll notice is that the black dots don't follow a one-to-one line. It turns out that the heavier you get, the more neutrons you have to cram into your nucleus to offset the number of protons apparently to be stable. However, you can also have processes where you have so many extra neutrons that you cram them in, and those elements will decay radioactively towards this band, and they will decay by emitting a beta minus particle, which we'll define in a second, but it basically converts a proton and converts a neutron into a proton, or emitting a neutron. And these things today, we can find them forming during supernova. We can find them, forming in neutron stars. The very final stages of stellar life for short-lived, very massive stars. And that's in fact where many of the elements in the periodic chart that we find on Earth today were formed, not in our sun. They come from well before our star was formed. There's also a band on here of proton-rich compositions. And the reason I'm telling you this is because during processes that happen when we are working with nuclear fuel for whatever reason, whether it's weapons or power, we make irradiation products. They don't push us as far out as these things. These things tend to be very short-lived, but they definitely push us on either side, oftentimes more commonly this direction than that direction on this band. So these guys up here will decay by beta plus. That's a positron. It's basically the emission of a particle with about the mass of an electron, but a positive instead of a negative charge, or proton decay. So just knowing which side of the black kind of line, if you want to call it line you are, will tell you what kind of decay. And when we get to heavier and heavier masses up here, it's more common to have alpha particle decay, which are helium-4 nuclei, which we'll define in a second. So there's some kind of rationality to that. So we give the three main types of ionizing radiation. We call it ionizing because the particles are energetic enough that if they interact with DNA or other cellular structures, they can ionize it, which means they can knock out electrons. Alpha, beta, and gamma. Gamma is the kind of radiation that is a very energetic light. They're photons. Alpha and beta. Beta comes in a variety of flavors. There are some other types too that don't get the Greek letters, but they're a lot less common, as we'll see in a second. And so we'll talk about this a little bit coming up, but how a radioactive isotope decays, how much energy it carries with it, how much mass it carries with it, is going to, and sort of how fast it decays, are going to be the main parameters that determine the risk or hazards associated with any one radioisotope. So they're not all the same. Some of them are much more dangerous than others, in part because of how frequently they decay, how much energy each isotope is carrying with it, each particle, I should say, and how frequently. So this is a chart that kind of shows you each one of these things. And it uses this notation where it tells you the Z, the proton number, whether Z goes up or Z goes down during the decay. It tells you the kind of particle. So we have the beta plus and the beta minus and the beta plus. Sometimes these are usually called beta particles, and beta pluses are usually called positrons. But some people will call them beta pluses. There's alpha decays, and so you can kind of read through them, and what you'll see is you have an element X. It's got an atomic number A, and it's got a proton number Z. In alpha decay, we're pulling something out. An alpha particle has a mass of 4, of which 2 are neutrons and 2 are protons. And that is helium-4 without the electrons on it. And so that gets emitted, if you remember back to that chart a couple of slides ago, at the heavier mass side of elements that are proton rich. And interestingly enough, these particles are pretty massive compared to, they've got a mass of 4. Let's say you're emitting one of those from uranium-238. Then that's a significant fraction of the total. It's almost a couple of %. Whereas in all these other cases, the masses of these particles are the mass of the electron. They carry a lot of energy, but they don't carry a lot of mass. So they interact very differently in terms of how far into tissues they can penetrate and how much damage they can impart along the way. So when we take an alpha particle off of something, we reduce the daughter isotope that comes from the parent has a mass of 4 less, and it has 2 protons less. And you can just kind of look at the periodic chart and see where it's going to take you to. When we do a beta decay, we're not changing the mass. So the atomic number stays the same, but we're taking a minus charge particle, we're making a plus charge particle out of it, right? So here's a minus charge particle, so the Z goes up by 1. So in essence, what's happening is that a neutron is emitting a negatively charged particle, an electron essentially, and be turning into a proton, and that's why this goes up. And positron emission is sort of the opposite. That's why the Z goes down by 1. A proton is emitting a positively charged particle to turn into a neutron. There's also something called electron capture. This is fairly rare, but probably the most famous element that does this isotope potassium-40, which is one of the progenitors of the progenitor of argon-40, but it's only one of the decay pathways for argon, is done by electron capture. What it is the innermost shell of electrons, so not the valence electrons, but the ones close to the nucleus. Every once in a while, one of them can become destabilized and tunnel into the nucleus. And so you're adding an electron to something which is basically absorbed by a proton to convert it into a neutron. Okay, and you'll see that this particular kind of energy can, but you can also capture external electrons in a very electron-rich environment, but it's also associated with the emission of X-rays. Gamma emissions is just light. This is usually accompanies one of these other decay modes, so that when there's decay, there's oftentimes extra energy that can't be carried off by the decaying particle, and so it's emitted as light. And then we have this one here, spontaneous fission, which is going to be a big topic for us. This is where nuclei break apart spontaneously, and this has a lot to do with the proportion of protons and neutrons and having enough of this material that it can self-absorb its own neutron emissions that it's making, and therefore break. And they rarely break into equal-sized fragments. Typically, this is a statistical process, and fission usually gives us things that are about 2/5 and 3/5 of the mass, plus a bunch of energy. This is the basis of nuclear fuel and nuclear weapons. So we're talking about that a lot. So this is just, I'm not going to go through this, but this is basically just lists what I just went through on that last slide. What happens during each one of these processes. And, you know, in essentially all of these things, we're making new elements, new chemical elements, because they have a different atomic number. So then this is just a way of looking at this in chart form, sort of summarized. You have a parent atom and it decays to a daughter. These are all the kinds of decays that we can have. Alpha particles change the mass by the most, which is obviously the combination of neutrons and protons. We can increase the proton number by emitting a beta particle. We can decrease the proton number by emitting a proton, or by electron capture or positron decay. And we can keep the proton number the same, but change the neutron number by emitting a neutron. It's a fairly rare decay mode. It's not one that we're going to focus on. This is just like to remind you again, another chart of the nuclides. I showed you that one a few slides ago, but this basically is an equivalent thing, but now just color coded for the type of decay. I think it makes it more clear to see that when we're on the proton-rich side of things, we emit protons, and when we're on the proton-poor or neutron-rich side, we emit beta particles. There's this region up in heavy mass where we start to produce a lot of alpha particles, and fission doesn't show up as its own thing on here until we get to very heavy masses. And so does anyone know the atomic number? I mean, you can look over here on the chart, right? The atomic number of uranium is 92. That's currently the heaviest naturally occurring element on the planet. There are no non-radioactive isotopes, but as I said before, the longest lived isotope is about the same half-life as the age of the Earth. So we still have that half of our original uranium left. So all these guys are up here in these heavy mass areas. And this is why you'll hear people talking about plutonium, which is over here, thorium, uranium. Those are the main things that are used for making nuclear weapons. There are other radioactive isotopes out there that have existed in the past. We do see them being formed in stars. They break apart, and depending on the stability of them, they fission with either short half-lives or long half-lives. I don't know what's going on with my computer today. I got all my bars, so who knows? Hopefully the Zoom doesn't cut out for the 4 people that are online. You know, this just gives you an idea, and you have to get to these things where you're emitting a proton or a neutron. You have to get really far away from this band, which we don't find too much happening in processes associated with nuclear power, or a little bit more so in nuclear bombs. But really, that's there for stellar processes, which are not something that we're talking about here. So the next thing to think about is the concept of an isobar. For a lot of those decay modes, except for the alpha decay modes, there's a lot of keeping the mass the same, but just changing the relative mix of neutrons and protons. And it turns out that there's something that we call an isobar, which is basically things that have the same atomic combination of neutrons and protons, so the same atomic mass, an isotope. There are plots that you can make like this for a certain mass. There's an arbitrary proton number, and then +1, +2, -1, -2. And if you do this for each of the isobars, so they're sort of like taking a slice through this diagram like that, you can plot up the energies, and you'll find a couple of different kinds of diagrams for even massed isotopes, which have either an even combination of protons and neutrons, or an odd combination of protons and neutrons. And the odd combinations are much less likely than even. But they're the most stable forms of chemical elements, and that's why most of the chemical elements we'll see are even, the abundance, I should say, of the even massed isotopes are much higher. And so this is just telling us the amount of energy that's holding nucleons together. And for any isobar, we can find one of two situations. One where there's what we call an energy well, meaning the most stable isobar, the lowest energy thing. Doesn't mean it has to be a stable element. It can also still be radioactive, but it's less radioactive. And the farther we go away from that nice combination, the more radioactive it gets, because the more energy we have associated with it. And depending on which side you're on, you're either going to emit a beta minus or a beta plus. Okay. And it turns out that when we look at the relative proportions, as I say, when we have odd combinations, that diagram becomes a little bit less energetically favorable to make one or the other two odd combinations, meaning odd protons and neutrons, or vice versa. And that helps explain the relative proportions of the elements. So there's a lot of different ways that people quantify decay rate. I'm telling you the CI unit, which is called becquerel, named after Henri Becquerel, who is often considered the discoverer of radioactivity, although Marie Curie did most of the work after the fact to kind of quantify where it was coming from and how it was coming from. So a becquerel is a decay per second. A Curie is 3.7 times 10 to the 10th, or 37 billion degrees per second, or becquerels. It's a huge unit. We never deal with curies of radioactivity. In my lab, I have microcuries of radioactivity, which, you know, we're licensed to have sort of 10 microcuries of this or that. Those are pretty safe quantities. I mean, you wouldn't want to eat it, but pretty safe. Radiation exposure is different than radioactivity. This is telling you how many particles are you experiencing and how much energy is associated with them. So that's measured in basically in joules, right? But we have SI units. So the old unit you'd hear people talk about all the time, like when I learned this stuff, were rads, which is 0.01 joules per kilogram. Rad is not the SI unit. Instead, it's grays, which whenever I hear this, I think about like, you know, the X-Files and that kind of stuff, but it's 100 rads. And so if you see like some of my old plots have stuff in rads instead of grays, they're related by basically a factor of 100. And again, they're joules per kilogram. Now, this is 1 joule per kilogram. Let's see. So radiation dose units are yet another factor. So you can have an amount of energy that's being imparted, but you can imagine as a dose, it's going to depend on things like what is the tissue that is being absorbed, how much of the energy can be transferred to it, how is the radiation coming at you, and so this has the same units as grays. It's called a sievert, okay? And the old unit, which you would hear all the time, like when you were getting an X-ray or something, are REMS. And it's the same relationship here. REMS and rads are basically 1/100th of a sievert or a gray. And we'll see on the next slide that there's some even more complications that we can do to distinguish this from this and figure out effective dose and so forth. But all of these units also, it's useful to know, just like anything else in SI, you can have millis or micros or megas or whatever abbreviation you want to put from stuff. So what you measure with a survey meter is usually becquerel. I mean, survey meters have these little dials on them that you can scale up by factors of 10 so that you can be with a very highly radioactive source, which is going to emit much more than a decay per second. The clicks that you're hearing are supposed to mimic the decay per second, but when you're near modestly radioactive material, it's just almost a continuous set of clickings. And that is measuring the actual particles. And you need to have different things on this head to be able to measure alpha particles, beta particles, gamma particles. And so the most common ones, the cheap ones you can buy, are just beta particles. which, like, for instance, in my lab, I have one that just measures alpha particles, much less efficient. It has, these things all have an efficiency, and you've got to be a lot closer to the stuff to see it, but you need a different kind of detector to measure stuff. So the becquerel is the number of decays. The sieverts is basically the dose that you're getting, and they're related to each other, but not just by the number of decays, by the amount of energy. So the thing about radiation and dose, which is really important, is that different biological tissues, ones that have more or less fat, more or less water, more or less protein, more or less mineral material like bone, have different relative biological effectiveness of absorption. And that's why, depending on the isotope, not only its chemistry, but its energy and the particle that it's emitting, it can give us different biological effectiveness factors depending on what it's interacting with. So this is other issue which has to do with how far can external radiation get into your body or any other material. And it turns out that the penetration depth of a material, of a particle into a material, is inversely proportional to its mass. So these alpha particles, which are really heavy, they carry a lot of energy. They're very disruptive. If you absorb an alpha emitter into your body and alpha particles are absorbed by your body and being produced in your body, they're really disruptive. But you can hold an alpha emitter in your hand. In the old days, I would bring a bar of uranium here and say, look, I don't mind holding this thing. And it would peg the Geiger counter, because these particles are stopped by your skin. They're stopped by a piece of paper. Beta particles can go through, these are much less massive, the things with the mass of an electron, the positrons and the beta minuses. They can go through paper, but they'll be stopped by sort of a centimeter thick of aluminum. And gamma particles can penetrate paper, they can penetrate aluminum, but they can't penetrate lead. So gamma radiation it carries a lot less energy with it, but it can go a lot farther in. So this is another part of this biological effectiveness. We have to look at the combination of the amount that we're getting and the energy of the particle and how far it can go in. And it's the difference between external radiation, obviously, and internal radiation. So if you ingest something that's radioactive, then the radioactivity is within you, and so it's really becomes a question of how much area around where that material is being irradiated by the radioactive radiation product. So this is a table that's showing you dose in rem. So remember, just divide by 100 to make them into sieverts. That basically tells you the different effects that you would get for radiation exposure. Right, so 0 to 25, reduction of white blood cells, 25 to 100, nausea, fatigue, changes in blood, 100 to 200, which is 1 to 2 sieverts, nausea, vomiting, fatigue, susceptible to infection, etc. Death possible, 200 to 400, fatal in half the cases. So that's basically a typical LD50, right? And there's a range here because it depends on the isotope and the mass and what's being decayed and so forth. Or what the decay products are. 600 fatal even with treatment. So in basically all cases. So that's 6 sieverts, for instance. And these kinds of high doses only occur when you're in proximity to a very radioactive material. But it's really the hazard or the risk that people sense with both nuclear power and nuclear weapons is that, well, I don't want to get that. But many more people are exposed at this level than this level in accidents or explosions or what have you, purposeful explosions. And so these are really the things that cause long-term sublethal effects, such as cancer. Doesn't take that much. So this is another concept that's related to this biological transfer to RBE, which is something called the LET, which is basically just the amount of energy that can be imparted along the linear pathway when radioactive particles interacting with solid material such as your body or a piece of wood or rock or containment vessel of a power plant, etc. And so you'll see that it increases on the way down. This is the amount of energy carried by that material. Penetration power goes down this list, but the amount of energy that it can impart goes up. And since sieverts are measured in energy units, that's really what we're thinking about in terms of hazards. So, and you can see all the various particle types here. this isn't a linear difference, right? These fission fragments, which are hugely heavy things, right? Think about, like some radioactive uranium-235 fissioning is making a significant amount of cobalt-60. That's a huge, heavy fragment compared to something like an alpha particle, which is a mass of 4 versus a mass of 60. So this isn't necessarily a linear scale the way it's written, but these heavier fragments, and especially the fission fragments, carry with them the most amount of energy, and they are especially hazardous when you have them internal. So if you ingest a material that is then either going to fission or is full of fission products, they can impart more energy when that decay happens. So this is just an example of during the period of above ground testing. I'm sure you're all sort of aware that the U.S. before it dropped this bomb, there was a little bit of testing, but then after we dropped our 2 bombs to end the World War II, there was like a flurry of activity of blowing stuff up, mostly first in the area we now call Micronesia. Bikini Atoll was considered the sort of ground zero, if you will. But there were a bunch of islands. The Micronesians that lived there were also like moved off to other islands, probably not far enough away, and then we bombed these islands. And then other countries were very soon behind us, especially the former Soviet Union, and to a much lesser extent right away, but later China and the UK and etc. A bunch of above ground testing that by the mid-60s, there was a treaty that signed to stop the above ground testing. Not all nuclear powers agreed to it, but Russia and us did, which was the vast majority of the above ground testing. We'll talk about the radioactive fallout from that and the hazards. That's the primary source of that strontium and yttrium I mentioned at the beginning. But this is just an example of, these are in REMs after an explosion, right? And you can see how far, these contours, this is 3,000 REMs, right? That's like huge, right? That's 3 sieverts. And here we are, that's like the next island over. And this is 1 sievert all the way out over here. And these are in miles from ground zero, right? So hundreds of miles. And that's the amount of fallout that was received during these above ground nuclear tests. And we'll talk a little bit more about them, the kind of dispersal that happens in plumes coming up. But we make fine particles, we make heavy particles. They're very high energy. We have condensation, metal droplets. And so the amount of radioactivity that falls out may be composed differently as we go downwind, as the things are falling out. Some fine particles get into the atmosphere, circulate around the Earth. And so above ground testing caused radioactivity pretty much everywhere on the planet to be much, much higher than it had been at any time before or has been since. And so just to give you an idea of the amounts that we're talking about. In that context, these numbers here don't seem all that high. So this is basically a chart showing you kind of in most generic sense how radiation exposure comes to people and why. Radioactive materials are just chemicals with the same chemistry as a stabilized substance. We're talking about radioactive strontium or stable strontium. It behaves like strontium. Strontium behaves very similar to calcium. So it accumulates within food webs in foods that have a lot of calcium. For instance, cow's milk is a big source of radioactive strontium when it's available in the environment. And the cows are eating grass that have strontium that they accumulated from the soil. And there are magnification factors like we have in food webs for other chemical elements, and then they accumulate in the human body. So that's one way to get radioactivity, is through ingestion of natural materials. We can also experience radioactivity from materials that we're interacting with, be them water or earth or air. So there are some radioactive isotopes that are gaseous. Radon is a common example. It accumulates in places where the rocks are relatively rich in uranium and the houses are not very well ventilated. So cool places like in the Northeast, they can accumulate high concentrations of radon. You can have high concentrations in your indoor air, and you can get radioactivity from that. So, as I say, we have to think about all the chemistry and all the stuff we've talked about already during the semester as exposure pathways for radioactivity. And the most common way that a person will experience enhanced radioactivity is not by being directly exposed to a radioactive source, is by eating a contaminated foodstuff or bathing in water that is contaminated. So I'm not sure why I have this slide in here twice. I think I don't know. I must have accidentally pasted it. So this is a slide about above ground nuclear testing. And this is a chart showing you 1945 and going up to the year 2000, USA, former Soviet Union, China, France, UK. There are a lot of other acknowledged nuclear powers now, like we all know that North Korea has them. But the quantity of tests that they've done, the ones besides this, places like Israel and India and Pakistan and whatever, the list goes on. But they came way after the above ground testing phase, so they don't contribute to global radioactive fallout contamination. And the number of tests are so small that they really wouldn't matter. These are sort of the main ones. So you can see that even amongst all these, the USA and the former Soviet Union did most of the above ground testing, right? That's all the black bars are above ground. And so these two powers signed a treaty that went into effect in 1964 and said, we're not going to do any more above ground testing. And as soon as they did that, and we'll look at some plots in coming lectures of what the fallout looked like, but the fallout of radioactive particles, which included radioactive strontium and yttrium and iodine and cesium, dropped off dramatically. It's still way higher today, right, half a century later than it was before. But just between the period between about 1950 and 1965, the incidence of childhood cancer on the planet, for instance, shot up by more than an order of magnitude simply because of the radioactive fallout. And this isn't just, in places like Bikini Atoll. This is all around the globe. Even though only a small fraction of the above ground test material was distributed everywhere, enough of it was that, even these two adversaries at the height of the Cold War agreed we're moving our testing below ground. Below ground testing, I'm not saying it isn't bad, because there are lots of potential problems: migration of isotopes into groundwater, fracturing of the subsurface. There are still ways of interacting, having people interact with the radionuclides, but they're contained to a much, much greater degree. I don't know why it's doing that today. And you can see by comparison, the small number of tests that China did, France, UK. France famously was doing its below ground testing south of here in French Polynesia. They took a particular place, Manoa Atoll, and they were blowing up their bombs underneath, and they pretty much destroyed that. And they did not sign on to this, and they were still doing that when I first moved here in the 90s. There was a lot of controversy about them transporting radioactive material by Hawaii and exploding them. It's pretty far. It's a couple days sail by boat, but even still, it took them a lot longer to stop their testing. It was in the mid-90s, whereas the U.S. and the former Soviet Union were pretty much done by 1990. So when I was a grad student, I spent some time at Lawrence Livermore Lab using their radioactive counters that were part of the nuclear chemistry group that would go out before and after a test, and they measure what was produced and bomb yields and so forth by doing soil analysis. And that was still active. That was in like the late 80s. So that was this period of time. And very interesting place to be. So if we think about our typical exposure for the typical American, and this is stuff you can get from the US NRC website, but about 80% of the average American gets most of their radiation from cosmic radiation, just radioactive particles coming off the sun and not being completely shielded by our magnetic field, and plus natural radioactivity that we talked about in rocks and air and water. Then about 20% comes from this combination of things, some sort of medical procedure that you're getting, consumer products. Tobacco, for instance, has a lot of polonium, which is the final decay product in the uranium-238 decay scheme, because they use phosphorus-rich fertilizers to grow tobacco and phosphorus-rich fertilizers to uranium. But you can see there's a whole bunch of stuff here: building materials, the kind of glass that's used in some glasses. Now we pretty much use plastic for that. But televisions, again, this was in the olden days when they had cathode ray tubes in it, watch dials, smoke detectors, et cetera, airport X-ray systems, the nuclear fuel cycle, meaning places that use nuclear power. It's not zero, and it depends. The order of these things can be different depending on where you live. but it's still, unless you're very unlucky, it's a small fraction of this, which is the majority of what people receive. And then you can see fallout from nuclear weapons testing and accidents. And again, it depends. If you're right next to one of these places, this is going to rise up for you. These are the typical values. This is another way of looking at that. So this is sort of in pie chart form, and this is, for instance, primary natural exposure for a lot of people is going to be this radon gas, which is radioactive, 3.5-day half-life, produced by uranium, whereas other terrestrial sources are much, much smaller. Again, depending a little bit on where you are, and this is sort of, internal stuff that you ingest in your food, even just eating bananas, which have potassium, or other potassium-rich foods, eating Brazil nuts, which have radium in them, etc. It accounts for about 10%. And it's not to say we don't think there's any safe amount of radioactivity, right? There's no amount that has zero hazard. However, the human body and most other organisms have developed the ability to repair the damage from radioactivity if the dose is small, right? So effectively, at some certain cutoff, the chances that you're going to have an adverse effect from being exposed to sort of a typical natural amount of radioactivity is relatively low. It's really the enhanced radioactivity that we're worried about, but at the same time, we don't think there's any amount that is safe, in terms of the ideal goal of getting to zero. Okay, so this is a chart just showing you one of the decay chains. These are chemical elements across the top, okay, and these are masses coming down. They just come here, then they jump over. This is the uranium-238 decay chain. Uranium-238 is the most common type of uranium. When it decays, it doesn't just decay once. It decays through each of these things are called daughter isotopes. Their half-lives are listed here. And you can see here they end up at a stable isotope. It turns out that uranium-238 ends up at a stable isotope lead-210. And the very last thing in this list, polonium-210, the thing I told you comes out of cigarettes, which I use a lot in my research, not cigarettes, but polonium, is 138 days, right? Relatively short half-life. And we're just going to be stable. Yeah, okay. And so what you'll see this kind of a trend here where all these half-lives down here are pretty short. They don't get shorter and shorter if they go down exactly, but kind of, right? So 4.5 billion years, 2.5 billion years, a couple of really short guys in between, 80,000 years, 1,600 years, 3.8 days, 3 minutes, 27 minutes, 20 minutes, 164 microseconds. So, but here's a relatively long one, 22 years. So shorter nuclides over here, longer nuclides over here. And the way decay chains work is that you make a standing crop of all these daughters from a certain amount of nuclear fuel, if you will. So if we have natural materials that have uranium-238, we're going to find all these things. And if it's undisturbed chemically, meaning it's not in the ground and being weathered and stuff being taken out or removed, then we'll find equal what we call activities of each of these isotopes in that decay chain. The activity is the amount of decay per unit time. It's defined as the number of atoms times the lambda, which is the decay constant. So things with short lambdas, like these things down here, are going to have less standing crop at a specific secular equilibrium. We actually use what we call secular disequilibrium. All sorts of processes can cause separation. So I use, for instance, the disequilibrium between thorium-230 and uranium-234 to date corals and coral reefs around the islands, because something about the process of forming corals from seawater separates these isotopes, and then over time they decay back to secular equilibrium. We can track that. And we use polonium to look at rates of degassing in volcanic systems. But so there's a lot of daughters here, and there are two other decay schemes as well. There's one with uranium-235 and one with thorium-232, which are the three most commonly natural. So now let's talk a little bit about the energy, which is really why people are so interested in using nuclear for either weapons or fuel. If you think about the amount of energy that's held in chemical bonds, like the enthalpy of formation of CO2, which you can look up in a table, and that's basically the amount of energy stored in carbon-oxygen bonds. It's about 393 kilojoules per mole. If we looked at the energy that is released by building a mole of carbon-12 just from the nucleons, which are sort of protons and neutrons, protons basically being hydrogen atoms, is about 8.8 times 10 to the 9th joules. So that's more than 10 million times more energy in the nucleons than in the bonds. And so we can liberate that, whether we're talking about this process here, which is fusion, or the more typical way we currently generate nuclear power, which is fission. That's really the lure of nuclear power or weapons or what have you. So the way we calculate the amount of energy has to do with something called the mass defect. And this basically explains nuclear binding energy as is you can basically look up the resting mass of nucleons and average nuclei in a table, and you can calculate this for yourself using the Einstein's equation of E equals delta mc squared. So this just shows you, here's the mass of a proton, here's the mass of a neutron. If we take carbon-12, which has a mass of 12 by definition, we can calculate the mass defect between 12 and 6 of these and 6 of those, right? And in atomic mass units, it's 0.9894, which we can convert into a nuclear binding energy by using the speed of light, this equals mc squared, and we find out, we also have this useful in those conversion units between AMU and kilogram, because the energies are usually expressed as per kilogram instead of per AMU. But we can calculate that the binding energy per nucleon, right, since this carbon-12 has 12 nucleons, 6 protons and 6 neutrons, is something like 7.6 million electron volts. It's a lot of energy that's holding that carbon together. It turns out in the periodic chart, there's sort of a split between the elements where we liberate energy by putting particles together. That goes from hydrogen all the way up to iron. And then once we get heavier than iron, and I'll show you this on a diagram, we have to input energy to keep building up mass, since that's not how they're formed. And this relates to sort of where and how, what processes elements are formed in stars. But this is basically the binding energy per nucleon in MeV. I know it's a little bit of a complicated plot. Just ignore this part here for a second. This is just showing you the area around the peak. And this is the atomic mass number. So what you'll see is that these things shoot up, right? And that means this is where fusion, nuclear fusion comes together. If you get the pressures high enough and the temperature high enough, which is very hard for us to reproduce on the planet, but for instance, in our sun, we take hydrogen and burn it to helium. That's the source of the energy. Our sun isn't massive enough, so it doesn't have high enough pressures to do anything else than that. But in more massive stars, you can keep cramming together nucleons and liberating energy until you get up here around Z equals 28. Once you go heavier than that, you have to add energy to keep going up in the chart, which is not how things are formed. This is the process I was talking about earlier, where we instead is sort of neutron or radiation processes near the end of stellar lifetimes, where we're making elements across this entire spectrum that are rich in neutrons that then decay to fill in this space. And so this part of the chart is what we oftentimes think of as the fission part of the nuclides, and these are the fusion ones, because these we liberate energy when we make them. These we liberate energy when we break them apart. And this is just a simplification of that same relationship, sort of showing you the fusion and the fission part of the chart. And just a little bit more about nuclear binding energy. And this is the rest mass of all 4 nucleons in a helium-4 nucleus, so 2 protons, 2 neutrons, and this is the rest mass of helium. And you can see that this mass is less than this. So putting these 4 dudes together to make them liberates energy. That's nuclear fusion. That's what powers our sun. If we try to put these together, or excuse me, take this and break it apart to make those, we're going to have to put in energy to do that. So fission, now I want to sort of focus on that heavier side. There's a few things that are related that are important with fission. One is we have to think about chain reactions, which has to do with having a certain amount of fissionogenic material. When it fissions, it also produces neutrons. If we have enough material present, we have what's called critical mass, and the neutrons that are absorbed by that amount of material create more fissions, which create more neutrons, which can go uncontrolled and create an explosion. And this is part of what we call the chain reaction, because one decay will produce more decays and more decays. And you have to have enough material present to make that happen. Now, on Earth, there are no naturally occurring fissionogenic materials that still have the concentration necessary to achieve critical mass for reasonable quantities of material. So uranium-238, for instance, does not undergo fission. Uranium-235 does undergo fission. Plutonium-239 and plutonium-240 both undergo fission, but we need to make these things to make them happen. The simplest thing, the very first radioactive material that was made on the planet that undergoes fission was enriching uranium-235 from its current present isotope ratio, a fraction of about 0.7% up to about 3 or 3.5%. If you're going to make a bomb, you want to get up around 80%. If you just want to make a nuclear fuel rod, getting it up to 3 or 5% is really hard to separate uranium-235 from uranium-238 because they're both very heavy. And we'll talk about nuclear enrichment, but it's an important point is because when we make enrichment, we also have to have a material, a complement material that's depleted. So we're going to have a whole lecture, we're talking about depleted uranium, which is a legacy that has gotten into weapons of various kinds, and it has other hazards associated with it. There's also related to this, having a critical mass and having enriched material is the fission products, the things that are produced when we make the fissions, and the which can be divided up into 3 things, right? The product of neutron addition, irradiation products that are produced in the vicinity of the nuclear fuel because of this neutron process. There's the products of the fission themselves. Sometimes these are also radioactive, sometimes they're not radioactive. Boy, that's frustrating. And then there's incidental, which means, let's say the metal components of a nuclear fuel reactor or whatever. And these categories are all a little bit different. So uranium-235 is highly fissile, but we don't have enough of it to spontaneously fission unless you purify it. Like if you're a natural uranium, if you obviously separate out uranium-235 and make it pure, it will spontaneously fission. It will produce enough fissions that then produce neutrons that cause more fissions that it can explode. And so these are the first atomic weapons were made from uranium-235. And the very first critical mass, which is the amount of uranium-235 enriched in total uranium required to initiate a runaway reaction, was first achieved on the planet in like 1940. This was Enrico Fermi's experiments in the area, in the Chicago area. And so, this is something that, at least in the modern era, was a human invention. But in the distant past, we had natural quantities of 235 that were a lot higher on Earth, and we had natural fission, which we'll talk about in a second. This is just the idea of the chain reaction concept, where decay produces neutrons and it's absorbed by other particles and other particles. And each fissile material has its own production factor. So in this cartoon, it's been artificially set to about 3, even though for natural uranium-235, it's more like 2.5. But it's hard to draw half of one of these. But other radioactive materials have different fission factors. But this is the idea of how you can get a runaway reaction in a chain reaction, because every decay begets multiple decays. So this is a concept of isotope enrichment. So we've talked about uranium-238. That's the dominant isotope. It's got half-life about the same as the age of the Earth. If you look at uranium-235, it's a lot less, 700 million. I mean, it's so long, 700 million years. But if you think about the age of the Earth, we've lost half of this. But here, we've lost much, much more than half, right? Because these things are cumulative. It cuts in half, and it cuts in half, and it cuts in half, and it cuts in half. So now we're down to much less 235 than we had in the past. And in the olden days, there was a lot more uranium-235 than 238, and natural uranium-rich deposits could become fissionogenic. It's also the genesis of the uranium-lead decay scheme, if you're familiar with that in geochronology, because this one decays to an isotope of lead-207, this one decays to lead-206. So we can look at materials that are rich in lead, galena ores, for instance, going all the way back to Earth's history, and tell when they formed by the relative amount of 207 and 206 they have in them. Because if they formed early on in Earth's history, in a relative sense, we have more decays of this than that, and nowadays we have more decays of this. So nowadays, there isn't very much uranium-235 and stuff. And so if we want to get materials to sustain a natural chain reaction, we got to enrich it way above its natural amount. This is the genesis of using centrifuges, which you hear about with Iran, and we're trying to block them from having centrifuges. Those are the things that are used to enrich the uranium. We'll talk about that process next time. But you need at least 3% uranium-235 just to make a nuclear fuel, and obviously much more to make a nuclear weapon. So, and their mass difference is really small. So as I say, to separate them, you gotta find a very specific process that allows you to do that. And the typical process is by taking uranium and making it into a gas. Even though it's very heavy, it turns out that uranium hexafluoride, uranium with 6 fluorines, is a gas at relatively low temperature. And so if you take some natural uranium and you turn it into this gaseous form and you turn it into these high-speed centrifuges, you can kind of separate the gas so that the lighter uranium and the heavier uranium kind of separate. You got to run these in what's called a cascade, where the output of one goes into another, It takes hundreds of these things, but after enough of them, because it's not a very efficient process, you can make materials that are enriched in uranium-235 and materials that are depleted in 235. When you think about that enrichment just going from 0.7 to a minimum of 3, that's like a factor of 5. So for every unit of enriched uranium you make 5 units of depleted uranium. So we make a ton of depleted uranium. And for a long time, it was just sitting around. And we'll get into that topic in a couple of lectures where U.S. government and then other governments decide, hey, we can make weapons out of this stuff. And so we're just blasting radioactive material into the environment. That's a different topic. So this is an example of a place called the Oklo Mine. It's in Gabon in Africa, where this was an organic rich shale deposit that formed 2 to 3 billion years ago. The organic rich material consumed the uranium because of redox ladder reactions, where uranium in the oxidized form is soluble and the reduced form is insoluble. So we accumulate high concentration of uranium. You go back a couple billion years ago, there was still a lot more uranium-235 around, so it could naturally fission. And this is just the lithology. There's this sort of various reactor zones, places where there was this organic rich material that had high enough concentration of uranium to be considered, or high enough with this being old, having enough 235 to go fissionogenic. We can't see the fission itself, but we can see the fission products in the materials around it. And in addition, there's still plenty of uranium-238 here, obviously, because that half-life is a lot longer. So that's why this place was being mined for the uranium-238. But they could tell that there had been decaying. So this is basically distance. In reactors 09 is one of the spots within this deposit that they gave them numbers that obviously was fissionogenic. And here we're looking at a whole bunch of different chemical elements where it's the daughter product, one of the isotopes, is enriched relative to the other natural isotopes, which gives the indication that there was radioactivity. And we can see that in a lot of these cases, these elements don't move very far, just a couple of meters. In a few cases, they move farther. This is a log scale, but it's the presence of these daughter things that tells us that we probably had fission going on. And so another thing that's related to fission is something called nuclear capture cross-section. It's just like it sounds like, with a cross-section is for every nucleus, it has a particular size. It has a propensity to accept a neutron or not. And we measure this as a cross-section. So some things like uranium-238, you can bombard it with neutrons and it's just not going to absorb. So it's got what we call a low cross-section. Whereas uranium-235 has a high cross-section, but the same number of nuclei, a much greater proportion of them will absorb. Plutonium isotopes have even higher, which means that if you want to get critical runaway chain reactions, as in the production of a bomb, then you're going to want to go with materials that have the highest neutron capture cross section, because then you need lower amounts of material to reach critical mass. So this is a table comparing a bunch of different statistics for 235, 238. You can see some other things, but I just highlighted 235, 238. The half-life, the activities, specific activities in DPSs, which are becquerels per microgram. The important things here are the thermal neutron and fast neutron capture cross sections. These are just neutrons produced in different ways, and we'll talk about that later. But you can see what the relative values are. These two numbers are high compared to these numbers, which are low, which tells us that that is, why 235 is fissionogenic and 238 isn't. And then you can come over here to plutonium and see that, for instance, plutonium 239 has even higher numbers than uranium 235, so it makes it better for bombs. It's a lot harder to make plutonium than it is uranium. So this is just what's called, it's showing you different distributions of neutron energy coming from different sources. So a thermonuclear reactor, a fission weapon, a fast reactor, sort of natural distribution that we would find from neutron sources in the environment when they exist. Modulated and unmodulated fission, meaning are we running it in heavy water or not, etc. And so you can slightly, not gigantically, but you can slightly tune the spectrum of neutrons coming off, which is also going to be a component of how fissionogenic a material is, along with the neutron capture cross section. I think, the gist of it is that when we're using nuclear fuel for nuclear power, we don't want it to undergo a chain reaction and to explode. We want to keep it controlled, and we want to pull the energy off. Whereas when you're running a bomb, you just want to blow stuff up, right? And so that's really a question of controlling this neutron spectrum and controlling the chain reaction so that it doesn't happen. So this is just an example of, an above ground test, one of the ones in Micronesia, and, explaining this difference between a bomb and a power plant. And there is this fission factor, which is, given with this Greek letter, which is not important, which is basically just some sort of probability, which is based on the distribution of neutron energy, that you're going to cause a fission with that particular neutron at a particular capture cross section. And so, like I say, we're trying to avoid that in reactors. So for the last few minutes, we're just going to talk about reactors, and then we'll talk about weapons another time. But there's a few things we want to look at. One are the neutron addition pathways to make fissile material. One is the incidental material, and the final thing are the fission products. So, in non-fission nuclear reactors, in essence, what you're trying to sort of do is make enough material to produce nuclear fuel that can then be used in something else. And the whole idea is that you're sort of harvesting this fuel from an irradiation source where you're creating, so for instance, a breeder reactor is a reactor that is designed to produce plutonium from target uranium atoms by neutron addition in a way that gives you can then pull it out and extract it and make enough plutonium to make a weapon. That's different. You can start with the same exact fuel. You can generate nuclear power and not plutonium so much, or vice versa. You can make a lot of plutonium and not so much nuclear fuel, just depending on how you run the reactor, how you modulate the energy of the neutron flux. So this is basically, the neutron addition pathway kind of shows that there are some other isotopes that are formed, these plutonium isotopes, and we'll look in a second heavier ones as well. So you can see where plutonium sits down here. So neptunium, plutonium, americium, californium, berkelium, these are the ones that, in lesser and lesser as you go up, that are commonly produced in nuclear powers. I mean, americium, for instance, is the common material found in most smoke detectors. Each one of these things has different nuclear capture cross sections. This is kind of a complicated diagram, but it shows you that in a neutron flux, in a breeder reactor, so we've already done the enrichment, made our relative amount of this, but now it's producing some neutrons, and we're absorbing those neutrons, and those are neutrons, some of those things are decaying, but oftentimes those neutrons are being absorbed, and then we'll have a decay that takes a neutron and converts it into a proton, for instance, by emitting of a beta minus particle. So we move along the periodic chart, and we make all these other things. So these are various isotopes of neptunium that are produced either from uranium 235 or 238. On this row, we've got plutonium. On this row, we've got americium. On that next row, we've got the californium. And with associated half-lives, right? And so the point being that in a lot of fission reactors, in addition to the fissile material, we're making a lot of these very heavy radioactive nuclei that have a higher capture cross sections. And the production of this stuff, even if we're not running a breeder reactor, if we're just running a regular reactor, it builds up in the fuel and it makes the fuel unstable. And so in many countries, what they'll do is take it and reprocess it. They'll remove this stuff and get back to this and reuse it. We'll see next time in the US, we don't do that. We just throw it away and we start from scratch, which is super wasteful and makes large quantities of stuff that then we have to deal with as waste. But that's the gist of what makes nuclear fuel, you know, unstable over time. And this is basically just a flow chart showing you that, you know, you start out with a certain amount of the uranium, how much of these various things can you produce? And, you know, if you're starting out with kilograms of uranium, you can make kilograms of plutonium. And that's, as I say, North Korea has been running breeder reactors. This was something that they signed this agreement with the US back in the 90s when Clinton was president, that they would dismantle all their reactors. So they dismantled the reactors for nuclear power, but not their breeder reactors. And so they started enriching, running the reactor in a way not to make nuclear power, but to increase the amount of plutonium. And you can make kilograms of plutonium, which you then obviously have to chemically purify out. So now that next topic is the fission products. And this is basically a typical fission profile. So mass number, and you can see here it's a log scale. So as I said before, if you take some 235 and you break it, you don't break it in half during fission. You actually get a lot less of the in half. You get stuff that's got a peak around 30%, or excuse me, around 40% and around 60%, 2/5 and 3/5. And there's a whole spectrum of chemical elements across the top. And so they're rich in materials, and these materials have a range of half-lives. It's just a table showing you the longer-lived fissionogenic isotopes, radioactive, strong cesium, selenium and rubidium, zirconium, technetium, palladium, tin, iodine, cesium. So these are on a higher mass peak. These are on lower mass peak. And you can see these half-lives, tens of thousands of years, millions of years. So once we make this fissile material, that radioactive material isn't going anywhere for a really long time, right? We also make a ton of short-lived radionuclides. The short-lived radionuclides are the immediate hazard. These are the long-term hazards. So this, and I've just got a couple more slides to go through. It's a little bit complicated of a plot, but it shows you time across the bottom. There's a chunk here that's in days, and then months, and then years. It's a quasi-log scale. This is a log scale in terms of curies. Remember, I said curies were this huge units, 3.7 times 10 to the 7th becquerels, which are counts per second. And so this is the pathway of decay. This is the total radioactivity of fissionogenic material. So it's ending up here at about 20 years. So in about 20 years, the typical fission products will have decayed by a factor of 100. Right? It's a lot, but it's not gigantic. Some of these things which have really short half-lives, they jump down really quickly. Some of the things with longer half-lives, like this thing here that's flat, right? It's not changing because it's got a longer half-life. You also see some of these things have inflections because one thing is decaying to another element that's then decaying to another element. And so we get a whole slew, that's the point, a whole slew of materials that decay over a bunch of different timescales. So oftentimes with radioactive material that's produced in this way, the first thing we'll do is just cast it, just let it sit somewhere for a year, and much of the short-lived radioactivity will go away. But a lot of these things, like these straight line things, are never going to go away on our lifetime. And this is just an example of, for instance, this technetium, which has got a 210,000-year half-life. It shows up as a straight line, right? Because it's not decaying over this time scale. So that was the last slide. We're going to talk more about these things in the coming lectures. Sorry to go a little bit long today. Are there any questions about any of this? Any questions here?